So, good evening, students. So, in the previous class, I was discussing about the continuous system. We saw the similarity and the difference which is there in between the continuous system and the discrete system. And then we started formulation for the bending of beam vibration for Timoshenko beam, which considers not only the shear force but also the rotary inertia. And already we had the energy equations in the formulation, kinetic energy and the potential energy. And in the previous class, we were applying the Hamilton principle to get the equation of motion and the boundary condition of the problem. So this particular, after the Hamilton principle, we'll be getting the partial differential equations because we have derivative with respect to the spatial coordinate x also apart from the time. So and one is a partial differential equation which is will be solving initially for the without force homogeneous equation. So we will be having associated boundary conditions also, which will give the solution unique solution that will be in the form of eigenvalue problem. So similar to the discrete system, we'll be obtaining the natural frequency and the mode shape. Here eigenvector will be in the form of eigenfunction because we should able to find out the shape of the object at every point onto the beam because it is mass is continuously distributed and we have infinite degree of freedom of the system. So I will share this slide again, which we left in the last class. So here little bit mathematics is there, but I think those are steps are very important to understand. So I will please look into the equations, and then once you are through with these steps, then any kinetic energy and potential energy is given to you, you should able to derive the equation of motion and associated boundary conditions of the problem. So this was the Hamilton principle, which we substituted the potential energy and the kinetic energy in this. So this is the kinetic energy term, I1 and I2. I3 and I4 is related with the strain energy or the potential energy, and this is the external work or external work done due to the external force. So I'll take up one of the integral I1. So here you need to see that basically is having two integration. One is with respect to x 0 to L, and outside there is another integral t1 to t2, which is with respect to time. If you see this particular equation, the variation of the y is having derivative with respect to time. So we need to convert this particular term so that we get the variation of y only, not its derivative. Here, two generalized coordinates are there, y and phi. So in the first term, y is there. So here we need to do the integration by part so that one derivative of this can be reduced. But the integral inside is spatial coordinate 0 to L. And we know the property of the integral that we can able to change the order of the integration without any problem. So shown the I1 here by changing the order, and understanding is there that outside we have integral 0 to L dx. and that will not play at any role at present. So I just kept the relevant integration, and once we do the integration, we'll substitute back that here. Then anyway, wherever double integration is there, double integration will come, or if single integration is there, single integration will come. So here I1 is basically double integration, but inside is integration with respect to time, because we need to do the integration by part of this term with respect to time. So this is the first part. My dot is the first part. So yeah, so one step here, what we are doing, interchanging the variation operator and the differential operator. That also we mentioned earlier that variational operator is similar in operation as the differential operator. We can able to change the order of this. Now this has come out. So now we can do the integration by part. So this first part as it is, then integration of the second part that is giving us variation of y, the limit t1 to t2, and then minus, then this is the differentiation of the first part with respect to time. This the extra term is coming, and this is the variation of the y. So there is nothing but the integration of this. So this is standard integration by part in one step. I've done it. Now this particular variation of y with respect to time t1 and t2, we have seen that the variation is defined is not defined for the at t1 and t2 at the beginning and the end of the time instant which we are considering. There's 0 at that point, so the first term will be 0. So we'll be left with the second term as it is. So this particular term we need to substitute back here, but because now you can see this is a time integration, and already the integration with respect to x is there. So we'll get I1 as double integral. What we'll do, we'll integrate, simplify all of them, and then we'll substitute one by one. Now I'll take up this one. This is identical to this one. Yeah, this is the I2. So here again, I want to change the, I need to interchange the variation and the differentiation here, and then do the integration by part. So this is the first integral as it is. And then the integration, the second one will give del phi. It should be del phi. It should be del phi. I think this should be. There's a mistake here. This should be del phi. So del phi is also not defined. Hello. Any issue? Any issue is there? Someone is talking. Hello. Someone is talking. Maybe you can mute if you, by mistake, you are done. Okay. So I hope. Yeah. So this is again not defined, because this is also one of the generalized coordinate, and this is the second part, differentiation. So when we differentiate, this will become derivative with respect to time twice and the variation of this. And this, because this is 0, so we're left with the second part only. So this is the I2. So I2 was similar to the I1. Now I3 is this one, in which now the spatial coordinate differentiation is there. So the time integration can be, we can keep it outside without any difficulty. We'll take only this at present. So that's why here integration with respect to x only is given. Here again we need to interchange this order of differentiation and the variation, and then we need to do integration by part. So this first part is the first part, integration of this with respect to x. So that will give us delta phi 0 to L, because now we are integrating with respect to x, minus differentiation of the first part with respect to x and the integration of the second will give this. Here this will not be 0, because basically delta phi is defined at boundary 0 or L position. So as in the time case it was 0, this will not be 0 here. So both the term we need to retain. But what is happening here? As I3 was double integral, because outside we have T1 and T2 integral. So you'll see that this will be single integral, outside time integral will come. This will be double integral because already integration with respect to x is there. So we'll get this term as single integral with time outside, and this is double integral as usual, as we have in the I1 and I2 also. In I1 and I2 both are double integral because this got cancelled. Then the I4, this one. So I4 is having multiple terms, especially here, because variation of the, we need to break this into two equations. So I4 is this equation. Now I'm breaking this into two equations. So when I'm bringing in the variation, so this is the first term, dy by dx, variation of this, and then minus variation of the delta phi. So basically I'm opening this particular bracket. This I'm keeping as it is, but I'm opening the bracket of the variation term. So variation of this minus variation of that will come. So I'll get two terms from this, and you can see this delta phi is having no derivative, so there's no need to do integration by part of this term. Only here variation of y is there, or differentiation with respect to x is there, so we need to do integration by part of the this underlying term with respect to x. And here we need to interchange the differentiation and the variation, and then we need to do the integration by part. So this is the first part. Then the variation integration of the second part will give us delta y 0 to L minus, then the differentiation of the first part. So this is the differentiation of the first part, and the integration of the second part is giving delta y. This term, last term is as it is, because there is no derivative involved here. So from I4 we got three terms. Out of three terms, the second term and the third term will be having double integration, because we have outside time integration. This we don't have the integration with respect to the x, so only the time integration will come on this. So this term and the previous I3, this term are having single integration. Rest of the terms are having double integration. Now I5 is having the required form del y. There is no derivative of the y, so we'll keep this as it is. So all these integrations now we need to substitute back in the, so this is the Hamilton principle with various integrations, which I already again I have written them, so that so I1 will be replaced by the previous integrations. This one, I2 will be replaced by this, like this. All we need to replace. And when we substitute I1, I2, I3, I4, I5 here, we will collect the similar terms. So delta variation of the y terms will collect in one place. So we'll be having one term from the potential energy, another term from the inertia, another from the external force, because the I5 is having delta y, so that particular term also. So These three terms are collected, which is having double integral as well as variation of the y. So this is very important that we have collected here the terms having double integral and the delta y variation. Similarly, here in the second one, we have collected the terms of variation of phi. And here also we have three terms. First two terms are from potential energy. This is from the inertia. So, and this is also having double integration because outside we have integration with respect to time. Last two terms are from I3, this term, which is having single integration because we have time integration outside, and this term I4, which is having single integration with respect to time. So those two terms are here. One is having phi y variation, and another is delta y and delta phi variations. So the aim should be clear that we collected double integration terms in one place having variation of y, no derivative of the y. We converted them by integration by part to delta y. Similarly, delta phi and rest of the terms we have kept here. So now, because these variation delta y and delta phi are arbitrary variations we are giving within the time t1 and t2, so they cannot be zero. And the y and phi are two independent generalized coordinate, so they can be chosen independent of each other. So to satisfy this equation, the term within this bracket or spiral bracket, we need to equate independently equal to 0. This term equal to 0 and this term equal to 0. We'll get the two equations from this. Similarly, variation of this is arbitrary. It may be 0 at the boundary or may not be. So to take care of all the cases, we need to equate here everything equal to 0, this one. Similarly, this equal to 0. This two will give us the boundary condition of the problem. So let us see the first two equations. So this is the first two equations of double integral will give us the equation of motions. So this is from the variation of y and this is from variation of phi. So these are the equation of motion. You can see this is a partial differential equation, quite complex equation. And the last two terms, this we independently equated to 0. So this is one boundary condition. This is the another boundary condition. We'll see these boundary conditions in detail. So this particular equation of motion is for Timoshenko beam case, in which we consider the rotary inertia in the kinetic energy and shear deformation in the potential energy. These two effects, the rotary inertia and the shear deformation, is called higher order effects. And these are considered only when the beam is having large size in the cross section as compared to the length also. So now let us see the boundary conditions. So in the boundary conditions, so at present we're not solving this. Let us analyze these equations, and basically this Timoshenko beam will not solve. We'll simplify this by ignoring the shear effect, which is called Rayleigh's beam. Even Rayleigh's beam will not solve here. We'll solve the Euler-Bernoulli beam, in which there is no higher order effect. We'll ignore the rotary inertia and the shear deformation, and that particular equation will solve in the closed form. Closed form means we'll get the equation which is having a final form of the frequency equation. So in the boundary conditions, because the beam, let us say cantilever beam is there, it will be having two ends. One is, let us say, fixed end at x is equal to 0, and maybe at free end, let us say, at x is equal to L. So here, either this quantity within the bracket will be 0 or this will be 0. And in this case, either this will be 0 or this will be 0. We'll see that both cannot be 0. I'll take up the simplified form of this, then things will be more clear. So what is this? This is nothing but the bending moment. What is this? This is the slope, bending slope. This thing is the shear force, and this is the deformation or the displacement. So the boundary conditions we'll see more detail in the subsequent slide. So when we solve these two differential equation, partial differential equation, we need to take care of these boundary conditions also, which is not there in the discrete system. In discrete system, the boundary condition comes implicitly in the form of the influence coefficient or the flexibility or the stiffness influence coefficient. So there is no need to satisfy the boundary condition separately, but here we need to satisfy the boundary condition to get the unique solution of this differential equation. And that's why in mathematics, this is often called boundary value problem. This is the summary of the various effects which we considered. Like in Timoshenko beam, we consider the bending, transverse displacement, rotary inertia, shear, all effects we consider. If we ignore the shear effect, then that particular beam will be having named Rayleigh's beam. If we are ignoring the rotary inertia also and shear effects also, then this is called Arnold-Bernoulli beam, which is in strength of material, you learn about the hypothesis of the Arnold-Bernoulli beam. So this is the summary of various effects of various kind of beams. So boundary conditions now we'll see in more detail. So as I mentioned, while solving the equation, unless we satisfy the boundary condition, we will not get the unique solution of the differential equation. And whatever the boundary conditions I mentioned earlier, there are basically two basic type of boundary conditions are there. One is the geometric boundary condition, which is also called essential boundary condition or imposed boundary condition. And they are basically geometric in nature. That means they are displacement or the deflection and the slope. So geometrical boundary conditions in the previous case, you can see there's a deflection. So this is the geometrical boundary condition. This is the geometrical boundary condition. Slope is also geometrical boundary condition. There is another kind of boundary condition that is called natural boundary condition or additional boundary condition or dynamic boundary condition. So they result from the moment, bending moment, and the shear force. So natural boundary conditions. So this is the bending moment. This is the shear force. So they are natural boundary condition or additional or dynamic boundary condition. So there are two types of boundary condition we define: geometric, displacement and the slope; natural, shear force and the bending moment. And these two boundary conditions supplement each other. And here we'll find that in this particular case we have 4 boundary conditions. So total boundary conditions will be having, because here even the number of boundary conditions we'll see once we simplify this. So basically we should have the 4 boundary conditions here. So here, let us say we are considering a beam with fixed at both ends. So axis is x this, y this. So this is the x0 position. This is x is equal to L position. So because this is fixed at both ends, so we expect that there is no deformation here. The displacement will not take place at the 0 position. So here the displacements at both ends are 0. Even because it's fixed, so slope also will be 0 here and here. So the slope are also 0. So these are the 4 boundary conditions. Now you can see that the shear force and bending moments are not coming here. So once these geometrical boundary conditions have come here, which are making 4 boundary conditions. So at the fixed end, we'll be having some shear force. They will not be 0. Bending moment also will be not 0. So they are not coming here. So those are not, we will not be imposing those boundary condition that they are 0, because actually they are not 0 in this clamped beam case. So here all boundary conditions are geometrical in nature. Now if we take one of the end as fixed, but other is hinged. So it's something like pin joint is there. The beam is joined by pin. So once the beam is joined by pin, what is the freedom this beam is having? The slope at this end will not be 0. So let us see the boundary condition, because this is the fixed end. So the same boundary conditions will be there at the fixed end. Displacement is 0, slope is 0. But at the pin end, now slope is not 0, displacement is 0. So when slope is not 0, so if it can really in slope, that means it is not having any bending moment to resist that particular slope. So here the bending moment will be 0 at the pinch point, apart from the displacement 0. So this is the change in the boundary conditions we find when we are having the pinch point. If both ends are pinned, then also similar boundary conditions will be having. So here displacements are 0, both and displacements are 0. And because both the pin joint cannot take moment, so they should be 0. Slope will not be 0 at both the ends. So another condition is cantilever beam, in which one end is fixed, another is free. So once this is fixed, the same boundary condition, displacement, slope is 0 will come here. But here at the free end, now it can have some displacement, as well as the slope also can change, because there is no constraint to restrict the slope or the displacement. So once it is freely moving up and down with changing slope, the bending moment will be 0, because slope can change, and the shear force will be 0, because displacement is also not 0. So here, when the free end is there, both the shear force and the bending moment is 0. So at free end, both the boundary conditions are natural boundary condition. At fixed end, both are geometrical boundary conditions. So you can see that in the previous case, we had 2 geometrical boundary condition, 2 natural boundary condition. Here, at one end, we have 2 geometrical boundary condition. Here, other end, we have both natural boundary condition. So various combinations can take place depending upon the boundary conditions we have. And then the last boundary condition, which these are the simple boundary conditions. So here there's a free beam. So it's something like there's no support at both the ends of this beam. And in this particular case, like if aircraft is moving in air, so the whole aircraft, if we are considering as a beam, so that kind of boundary conditions we can consider. So because both our ends are free, they can have displacement and the slope. So bending moment and the shear force will be 0 at this end and this end also. So both the ends will be having bending moment and shear force 0. And here for free case, we have all the boundary conditions as a natural boundary condition. There is no geometrical boundary condition. And in again, we already seen in the fixed case, all were geometrical boundary condition and no natural boundary conditions are there. So, but in totality, we should have 4 boundary conditions to solve the differential equation. So, eigenvalue problem we'll take up now. But eigenvalue problem will be, as I mentioned, for the Timoshenko beam will be too complex to handle in this course. So we'll simplify the Euler-Bernoulli beam to the Timoshenko beam to Euler-Bernoulli beam because Timoshenko beam, the shear deformation, rotor inertia makes the equations more complex. So here the cross section of the beam, if it is small as compared to the length, then the rotary inertia and the shear deformation can be ignored. That is very important. When we can apply this this Euler-Bernoulli beam hypothesis, when the cross section is small as compared to the length. So then in that particular case, the beam will be thin. So the rotation due to the small element will not be having that much inertia. So rotary inertia can be ignored. Also, the shearing effect will be less. And for eigenvalue problem, anyway, we need to consider the force equal to 0. So now I'm simplifying here the equation of motion which we got using Timoshenko formulation. So these two equations we got earlier. This is the first equation. This is the second equation. So now we will be simplifying them. So what I'm doing here, this equation I have rearranged. I have put the inertia term and this external term right side. So this is the step. So these two terms I have kept in the right side. This equation I differentiated once with respect to x. What is the motive of that doing that? Because if I differentiate this, so this will be double differentiation with respect to x. This will be in differentiation with respect to x. This also got differentiated with respect to x. Now, if you see this term is same as this term. So, in fact, I want to combine this two equation. So, by differentiating this term, I got this. So, I replace this term with the this right hand terms. So that has been done here. You can see this term has been replaced by that. So these two terms came here. Okay. So now this is the we have combined this equation. There is no simplification till now we have done here. We have just combined these two equations. If you see the order of differentiation of this is if you see the order, I think present because phi is related with y, and y phi is related with y like this. So in effect, this is a fourth order differentiation. But let us simplify this, then things will be more clear. So now this k which we introduced, the parameter, was the shear deformation parameter. If you remember, when we introduced the shear force, then we introduced this k term. So this is related with the shear effect. So if we ignore this k, this term will be dropped. So if we drop this, and for free vibration, we are dropping the p term also. So these two terms, when we drop, we got this equation. Now, because now shear effect has been ignored, because K we are ignoring. So once the shear effect is ignoring, the beta will not come between the so whatever the relations we had between the dy by dx, that was nothing but phi plus beta, both were there. So beta will disappear from this relationship. So then phi can be replaced by dy by dx. So this phi can be replaced by dy by dx. So if we replace this, this will be now fourth order differential equation. This term is as it is. So this is the elastic term, because you can see Young's modulus is there. So this is the elasticity term. Here y double derivative with respect to time is there, m. So this is the inertia term. So it's similar to whatever the equations we have in the discrete system, mx double dot plus kx, but this is in the more complex differential equation form. But basically this is a balance of the shear, the inertia force and the elastic force. And this equation is for Euler Bernoulli beam having pure bending without higher order effect. So the rotary inertia and the shear effect has been ignored here. Even there is no external force we are considering for time being. Now we'll see the boundary condition. So we had, apart from this equations, we had the boundary conditions also. That also we need to simplify now. So these were the boundary condition corresponding to the Timoshenko beam formulation. So here now, because phi, this between these two relationships, there is no beta now because shear effect has been ignored. So phi will be dy by d phi. So the bending moment, which we define as EI or del phi by dx, this phi can be replaced by this. So bending moment relationship, you are already familiar with this form in which EI del square y by dx square is there. Then the shear force, yeah, this is the K prime term I was talking about. So this term, now we need to simplify the shear force term. So in the equation of motion, which was in the previous equation was 520 equation. This is the term which is shear force actually. This whole term is shear force, because beta is related with the Timoshenko beam dy by dx. So this is the shear force. So if we replace this term as shear force and ignore the that is k term is here, this is the radius of gyration. K is the radius of gyration. K prime is the shear correction factor. So if we ignore the K rotary inertia term also, and this we write as a shear force with this one. So this is as it is, and this we are writing as shear force, and this is equal to 0. So shear force can be expressed as negative of this quantity. And when we note the shear deformation, shear force is there, but we are not considering the shear deformation effect. So this phi can be replaced by dy by dx. So this will become, so this equation is familiar with you, that shear force is the basically third derivative of the y multiplied by EI. Here this has been kept outside because EI can change with x. So this formulation is more general. So now with this understanding, because this is, now you can see, as I mentioned, this is the shear force. So this can be written as shear force. So the boundary conditions now will simplify like this. Again written the Timoshenko boundary condition here on the previous slide. So this I'm writing as a bending moment. This as slope. This I'm writing as shear force. This is the deformation. So with the Euler-Bernoulli beam boundary condition, bending moment we have defined now EI del square y by d phi. So here, because of the beta term is ignored, so phi can be replaced with dy by dx. So this will be double derivative. Similarly, the shear force, this one we can able to write. So this is the boundary condition corresponding to this differential equation we got for the Euler-Bernoulli beam. So now we could able to simplify the boundary condition also of the problem. Now let us start the eigenvalue problem or the solving the differential equation. So this is the differential equation for Euler-Bernoulli beam case, in which this is the elastic force, this is the inertia force, where we have shear effect ignored. So beta is not coming between these two. So total slope is nothing but the bending slope only. So this is a partial differential equation of fourth order. Y is having differentiation with respect to x as well as time. So we are using separation of variable method to solve this. So we are assuming a solution yxt as capital Y, which is function of x alone, and f, which is function of time alone. So this is standard separation of variable method. So if we substitute this here, because here in the first term there is a differentiation with respect to x is there, so only the y, capital Y will get differentiated. So if you see here, capital Y will get differentiated. Ft will come out from this because there is time function. In the second term, because this is derivative with respect to time, so y will be as it is, capital Y will be as it is, but Ft will be getting differentiated with respect to time. Now this equation will separate such that in one side we'll keep all the terms containing x function, and other side will keep all terms containing time function. So you can see that if I divide by y, this can come this side. M can also be function of x, so that also I will take on this side. Ft I have divided so that this goes this side. So now this term contain this function of x. There is no term which containing function of time. Here all terms are function of time. So in one side we have function of x only, another only time. So how they can be same? They can be same only when they're equal to some constant. And here that constant we are taking as positive constant, omega square, because this positive constant will give us a harmonic motion which we require for the free vibration which we are solving it. So the consideration of this positive constant is based on the harmonic motion we need for the free vibration of this. So if we equate equal to a positive quantity omega square, so I'll get two equations. One equation is this, which gives the harmonic motion. Second equation, if we equate the left side with the omega square, I'll get another equation. So now this equation is should have written this as, now is no more partial differential equation, because now this is, yeah. So now this is a differential equation of fourth order. This is ordinary differential equation now. So that fourth order differential equation, partial differential equation, we could able to convert into two equations, and now our interest is on this equation. And this is because force is not there in this, so this is a homogeneous ordinary differential equation. Now it is ordinary differential equation of fourth order. So the solution of this is what should be the constant which we have chosen. Okay, so we have chosen the constant, but what should be the constant for which this differential equation will satisfy? This also we need to find out non-trivial solution, non-zero solution, which will satisfy omega. So we'll find that there will be some fixed value of omega for which this equation will be satisfied, and we need to satisfy the boundary condition of the problem also. So not only the differential equation, but also the homogeneous boundary condition, because there also we are considering no forcing term. And this is the eigenvalue problem, in which we are seeking the solution at what omegas we have the solution of this, which is satisfying not only the boundary condition, but this differential equation also. And that is a eigenvalue problem. In the discrete system, the eigenvalue problem was in the form of matrix. That was linear homogeneous equations. Now, in the continuous system, we are getting the eigenvalue problem, which is ordinary differential equation. I think at the beginning of the lecture of the continuous system, I mentioned that the eigenvalue problem for the continuous system will be ordinary differential equation. Equation of motion is the partial differential equation, but eigenvalue problem is differential equation, and that's why the solution is slightly difficult. And this omega is called the characteristic value for eigenvalues, as we have defined lambda earlier. So here omega is same as lambda. These are they are related with the natural frequency, but in mathematics this is called eigenvalue. And the solution which will be getting y, this function, is a characteristic function or eigenfunction. So earlier we had eigenvector. Now these are eigenfunctions because they are function of x. Because at any point on the beam, if you want the value of y, we should be able to get. So here we'll be getting the mode shape as in the form of eigenfunction. And as in the discrete system, they will be having one-to-one relationship between the eigenvalue and the eigenfunction. So for a particular eigenvalue, there will be corresponding eigenfunction. And so that means for a particular natural frequency, there will be particular mode shape of the beam will take place. Here this omega value will be having infinite values. In the discrete system, we had from eigenvalue problem n number of eigenvalues, but here we'll find that we'll be having infinite number of such possibility for which this differential equation will be satisfied along with the boundary condition, and those will be related with the natural frequency. Okay, so this eigenfunction, again, the magnitude of the eigenfunction, or whatever the amplitude is related with the eigenfunction, will be arbitrary, but the shape will be unique. The shape of this will be unique, as we had in the discrete system. Shape of the object was, the mode shape was, eigenvector was unique, but the shape or the relative magnitude was unique, but absolute magnitudes was not unique. So same thing is valid here also. The magnitude part will not be unique, but the shape will be unique. And this is whatever the eigenfunction we got with the constant. It's called natural modes. Here also the normalization, as we did of the eigenvector earlier, will be valid. If you normalize eigenvector, then those vectors are called normal modes. Otherwise, we can call this as a natural mode, and they are characteristic of the system also. So I think I have some time to finish this boundary condition. Yeah. So quickly we'll see the same boundary condition as we had earlier. Now only change will be because now we have defined the solution like this. So now earlier we equated the y, small y, equal to 0. Now because this is a time dependent terms will be coming, they will not be 0. So only the capital Y terms will be 0. So all other places where the small y was there, capital Y will come, like fixed case, this capital Y and capital Y at 0 and x position will be 0. This is slope at both the ends are 0. So this fixed case, both displacement and slope will be 0 at the ends. This is a fixed case. Then fixed on the hinge. Then in this case, here we have displacement 0, but at free end, at the hinge end, we'll be having the bending moment 0 and the shear force 0. Sorry, this is at the free end, this end only. The bending moment will be 0 and the displacement will be 0 here. Here displacement is 0, slope is not 0, and bending moment is 0. Here both y and the derivative with respect to y will be 0 here. In the cantilever case, we have shear force 0 here, which is given by this or this, and the bending moment also 0. So this also. So here the same y and the slope of that will be 0. So these are similar boundary condition, except now we are writing in terms of the capital Y eigenfunction instead of y displacement, because now we assume the solution like this. So rest of the things will be same. So in the next class, we will take up the solution of these eigenvalue problem. And before that, because in the discrete system, we define the eigenvalue problem in a general way. So same thing here also will be defining the eigenvalue problem in a general way first, then we'll solve the eigenvalue problem for specific cases, so that the common property we can analyze in the generalized formulation, which is applicable for several cases. So I'll stop here because this was more on the formulation part. So if you have any questions on the today's lecture, you can raise your hand. Okay. Okay, so there is no question. So hopefully by next class we'll get into the specific problems. Then things will be more clear. At present, the formulations are more general in nature. So in the next class, maybe we'll be solving eigenvalue problem examples. So and then we can able to correlate how the actual form of the equations are taking place. Okay. So I think if there's no questions, I will quitting now.